Tom covered the aspects about monitoring for HABs. And then Bill went into the first step on optimization related to particle removal in terms of cyanobacteria cells, and then absorption of extracellular toxin using powdered activated carbon primarily. So I'm going to kind of continue that discussion, but focus more on the oxidation aspects of cyanotoxin destruction. So let me go ahead and load up my presentation. I'll also say that, and Bill mentioned it before lunch, for the workshops, we do have suggested response files that we'll put into the directory after the training. I hate to call them the answer sheets because they do have some of the answers, but they are suggested responses because oftentimes in this work there are alternative solutions, and we haven't identified all of them. So there are some of them in there. So with that, I'll go ahead and share my screen. All right, I'm going to talk about optimization from the standpoint of using a process that all plants are familiar with. And it really kind of revolves around the concept of disinfection or CT. But it also can be referred to as oxidation. Kind of give an overview on the process. There was a part here also on review of disinfection CT concepts. I'm just to save some time on the presentation and get into the workshop, I'm going to skip most of that, but I'll mention a few points when I get to that area. I'm going to spend more time really reviewing an Excel spreadsheet that can be used to determine how effective your oxidation process is for removing cyanotoxins, or it can be used to come up with how much basically contact time and oxidant residual you need to address a specific HAB event. And I'll show a couple of the screenshots from the spreadsheet. And you'll get some hands-on experience using it in the workshop. This table here is a summary of the effectiveness of common water treatment oxidants for cyanotoxin oxidation. And this is pulled out of a document that Tom Waters authored with EPA. It is included as a reference document in our training materials. Some of you may be familiar with it if you've reviewed or looked ahead in terms of planning for addressing cyanotoxins with an oxidant. And it's a good summary in terms of the typical oxidants such as chlorine, chloramines, chlorine dioxide, potassium permanganate. Then for those plants that may have ozone or planning to put in ozone, and then more advanced oxidation. And then for across the top of the screen, it talks about, referencing four specific toxins from anatoxin A to cylindrospermopsin, microcysteines, and saxitoxin. So if you look, if we look at microcysteines, which is pretty common in most blooms, we can go down and see that chlorine is effective. Chloramines, not so much. Actually, if you just scan across the table for chloramines, they're not that effective, or there's not information. Surprisingly, chlorine dioxide doesn't appear to be that effective either. Permanganate is effective for microcysteines. Ozone very effective, and then advanced oxidation is very effective as well. But if we scan over to looking at anatoxin A, which is starting to show up, at some facilities, and that was the toxin that impacted the Columbia River. We see that chlorine is not very effective for destruction of antitoxin A. Chloramines, no. Chlorine dioxide, typically not effective at normal doses. But we get down to permanganate, effective, ozone effective, advanced oxidation effective. So it's really important to know what toxin you have and whether it's intracellular, extracellular. But knowing and using this table and knowing what you have, you can plan your strategy a little bit better. So cyanotoxin destruction through oxidation follows the same approach as we use in treatment plants for achieving our disinfection from pathogens. In other words, it's based on a CT concept. So C being the concentration of the disinfectant, or in this case, oxidant, times the amount of contact time. And this table is also pulled out of Tom's optimization document for HABs. And it's just one example. It's just one of the tables out of that document that shows the required or the effective CT required based on certain specific concentrations of, in this case, microcystin LR. And it is affected, CTs are impacted, similar to disinfection of pathogens with chlorine anyway. It is impacted by the pH of the water as well as the temperature of the water. As I mentioned, it is based on the CT concept. So measuring the oxidant concentration in milligrams per liter. In this case, we're using an oxidant is used in place of disinfectant for this application. And then measure the time the oxidant is in contact with the water. And the combination of those two factors will give you your CT. It's essentially sort of an oxidation strength or power, ability to destroy the cyanotoxins. I did have a series of some other slides in this presentation that are kind of a CT review. I've moved them to the back of the presentation. They're still there as a reference. But to save a little bit of time, as I said at the beginning, I'm going to skip over that. And it is the same. I will say this: it is the same. Use the same approach for cyanotoxin destruction using CT as you would apply it for pathogen inactivation. So all of the rules, all the guidance, all the guidelines for CT for pathogen inactivation, the same ones follow for cyanotoxin oxidation. I did want to talk a little bit about permanganate because a lot of us are familiar with using chlorine in treatment plants for disinfection. Some of us are familiar with feeding permanganate, but not everybody. So, and as I showed in the previous table, permanganate can be pretty effective if you have some specific toxins like antitoxin A, or if you maybe need to apply a multiple barrier approach where you just can't get enough destruction with chlorine and you may need more with another oxidant. So I have a couple slides talking a little bit about permanganate. Feeding permanganate requires an understanding of your available contact time, what the oxidant demand of the water is, dose control to achieve a target residual, and also importantly is avoiding overfeeding, which can create not only color, but it can also create turbidity and can be a secondary impact and make things worse in your plant. The picture to the right here is from a small packaged plant that actually was having issues with manganese in their water, and they were feeding permanganate at a moderate, I would say a moderate dose, but the challenge that this plant had, as you can see, it's a packaged plant, so it does not have very much contact time. So at the dose that they were feeding that permanganate, they were getting a lot of color. Typically overfeeding shows up as a pink to red color in the top of their clarifiers and moving all the way over to the top of their filters. So that's the end result if you feed too much permanganate. And again, it's plant dependent. A lot of times depending on how much contact time you have. Feeding considerations, permanganate's available primarily in two different products. First, the KMNO4, potassium permanganate, kind of was the initial product that was put out on the market. But for quite a while now, there's been a liquid product, sodium permanganate, that's some plants prefer to choose to use. They, both are dosed similarly, but they have, you have to account for concentrations and dilutions, that sort of thing. The liquid is easier to handle and feed, but it's more expensive. So you pay for the convenience of feeding a liquid versus having to feed a dry powder and mixing up in batch tanks and that sort of thing. The feed locations should target, where the extracellular toxins are prevalent. So typically you would feed it, where you have extracellular or dissolved toxins. However, in the case of permanganate, post-application is typically not used just because of the secondary impacts that I talk about at the beginning of the slide. So it's usually fed at the front end of the plant. The estimated dose can be determined visually. Operators look for a slight pink color in their sed basin sometimes. So it's okay to carry over a little color because typically that'll go away as it goes through the filters. Jar testing is also an excellent process control test to determine demand and dose. And the picture to the right here shows a permanganate demand test where raw water was dosed with permanganate. Starting in jar 1, essentially no permanganate. And I don't remember the exact doses, but as you can see, as you go from left to right, you start getting a change in color from kind of an orange brown color, indicating that you've got a manganese particulate in the water to the point where it starts getting more pink to red, which indicates that you definitely have a permanganate residual in the water, and maybe too much. More than you really need. Because if you're given enough time, if you start seeing the permanganate show up, that means you have met the demand of the water and you're carrying a residual. For cytotoxin applications, determining the required CT, you use basically that spreadsheet that we're going to be using in the workshop. But it does require, just like with CT, when we're applying it to chlorine, it does require us to be able to measure the permanganate residual in the water to determine a CT. So a couple different approaches on this. Permanganate residual, in water can be determined first by developing a calibration curve, and there's a procedure for that. One of the common vendors, maybe the most common vendor for permanganate products is a company called Caris Chemical. They have a procedure on how to do that. These images are clips from their procedure here. So it basically shows where they developed a calibration curve where they had different concentrations of from a stock solution of known concentration of permanganate in the water. And they used a spectrophotometer set at an absorbance of 525 nanometers. So they can develop, a relationship just by reading absorbance, you can get a pretty good idea of what that residual is in the water. So in this particular example, if the absorbance is 0.0275, going over to the line of best fit and then going back down, we can be pretty sure that the concentration of the residual in the water is around 0.7 milligrams per liter. Another handy little thing to know is that actually the chlorine DPD method can also be used to estimate permanganate residual in the water, assuming there's no other oxidants present, because the other oxidants like chlorine would be a positive impact on that test result. So if there's just chlorine residual in the water or just permanganate residual in the water, it's pretty close. It can definitely be used as a way to indicate permanganate in the water. There are, with the sort of increased usage of permanganate for different process objectives, there are going to be more online monitors available. There's several vendors that provide monitors. Our guidance here, since they're relatively new on the market, is to really kind of look closely and assess what their analytical method is for measuring it, and what the user experience has been with the instrument. And if possible, highly recommend a full-scale trial to see how the instrument works in your plant. It is, as I said, marketed for a lot of different applications, all the way from manganese oxidation to organics reduction, zebra mussel, and potentially cyanotoxin reduction as well. Now I'm going to switch gears here a bit and talk about use of the spreadsheet, the cyanotox spreadsheet. This was essentially a tool that was developed by Hayes and Sawyer engineers and Craig Adams, professor from St. Louis University, through a sort of a cooperative project through AWWA. And it happened, the development happened after the Toledo HAB event. And so the industry recognized that that we need tools. And this is one of the important tools that came out of that work. The spreadsheet is available. We're going to be using it in our workshop. It's available for, and you'll have a copy of it with our materials. It's also available as a download from AWWA. The most recent version, from my understanding, is version 3, and that's the one that we'll be using. Every tool like this that's developed has certain caveats and disclaimers. I'm not going to read through all of these, but there are certain ones that are important. I mean, the purpose of the spreadsheet is to assess the impact of oxidants for destruction of dissolved or extracellular toxins. So that's primarily how it's used. The most conservative way to use the model is the CT-based approach, which I'll cover here in a minute. But I encourage you to kind of read through that section of the spreadsheet that talks about how to use it, maybe how not to use it. As far as the instructions, there is an instruction tab in the spreadsheet. Again, I encourage users to read that first. It doesn't take too long to kind of read through the steps and how to use the spreadsheet. And the calculator includes two main approaches to basically assess your system. There's a CT-based approach, which is most often used. It's really the only one I've ever used. And then there's more of a dose-based tab, which I have not really used that much. There are 7 instructions steps that I'll describe as we go through this. And in terms of how to use that CT-based approach, which I'll describe in the next slides, keep these 2 points in mind. So how would you, as an evaluator or a plant operator, use this spreadsheet? Well, the first way you could use it is you could enter your cyanotox type. What kind of toxin do you have? And the concentrations of that toxin coming in to your plant and what your target is going out. So it knows basically what's coming in and what you want to target going out. You would enter in what type of oxidant you're using, for example, chlorine or permanganate. As the table indicated, you need to enter your pH and your temperature. And with that information entered, it will tell you what the required CT will be needed for your plant to get that level of performance. The second way that you could use the spreadsheet is you enter a CT. You know what CT that you can achieve from your plant, or you predicted that. You enter the type of cytotoxin and the initial concentration. What's the concentration coming into your plant? You add what type of oxidant you're using, you add your pH and your temperature, and it will then tell you what your final cytotoxin concentration is. So keep in mind that there's two ways primarily that we use the spreadsheet. And both of these are going to be used in the workshop coming up. So I'm just kind of showing some screenshots from the spreadsheet using the calculator. These are the common inputs that I just mentioned. You can select the type of toxin, or there's basically 4 choices with a little bit of information on those. Microcystin LR is a pretty common one. From a general perspective, but if you have antitoxin or cylindrospermopsin, that might be your choice as well. And what I tell people when they're just getting familiar with the spreadsheet is play around with it. Just see, well, what impact would it have if I had microcystin versus all of a sudden if I get cylindrospermopsin showing up? Does it require a much different CT? The best way to find out is go in and try it. The option to select the oxidant type. We've got free chlorine, ozone, permanganate. It shows the typical ones listed there. And then once you have entered that information, you follow basically 6 steps to enter additional information. So I mentioned that the most common tab that's used is the CT-based version. And the inputs to this tab are required to basically predict the final toxin value based on the known CT. So that was that second example, or that case that I presented earlier. So that's where you would enter that information. In this example, it shows that we're using that CT value, which is recommended. And we entered in we already know what our CT is. We put in 120. Second bullet here, inputs are not necessarily required to predict an effective CT required to achieve your target toxin in this particular location. Important to note here, when you look at the worksheet, the step 7, it doesn't show it here in my slide, but a lot of these input areas have little windows that you can toggle and select different choices. And this is one of those. So if you click on the little arrow, it'll say select CT value, which is recommended, or you can select a residual and a contact time. So in our workshop, we're going to be using this first choice. In the second example of the workshop, you're going to be actually calculating out a CT and entering that CT number. So keep that in mind. The CT value options. So you basically enter a value based on plant design and operating conditions. You can use a sort of a trial and error approach to find out the conditions to achieve your target. So if you're not totally sure what CT is required, you can try some different values to see if it gets down to the level you want leaving your plant. A little bit of guidance on determining CT. So you really kind of need to think about this a little differently, thinking about a HAB event. So you might need a higher oxidant residual than normal. And so you might have to consider factors. If you bump up your chlorine residual, what kind of impact that's going to have, operating at higher residuals. Do you have the chemical feed capability to feed at those higher residuals? And then during a HAB event, longer contact times may be possible. So that might be an option to give you more CTs. So maybe reducing your plant flow might be an option. You might be able to come up with additional oxidation, additional contact volume for oxidation. So again, this is, a what if scenario, thinking a bit out of the box. So the last part here I'm going to show you is kind of like where you get your results, the results from entering all that information into the spreadsheet. The gray area here shows values that were entered. And then I sort of identify them as the key results. So the first kind of the yellow box, I guess, arrow and pointing to the top level of information, that it shows you at that point what your final cyanotoxin concentration is predicted for this particular example. So it's showing that the conditions resulted in a final concentration down at 0.2. And that's based on the CT value of your system. So if you entered a CT number into the spreadsheet and an initial concentration of toxin, in this case, we look up here in the gray box, it was 10 micrograms per liter. Under those conditions, it said it would get you down to a 0.2. And we'll reference these numbers relative to the health advisory when we do the workshop. The other, what I refer to as key results, is down here, the effective CT to achieve the target. And that's shown in the last box here. In this particular case, about 104. And so in that case, we would have entered an initial concentration and a desired target. And then it's going to tell us, well, to achieve that, you're going to need a CT of about 104. So it's basically milligrams minutes per liter. So it's milligrams per liter times minutes is the units. Our experience from using the spreadsheet is it's best to apply a safety factor. And the safety factor that we have commonly used is 2. So in this particular case, apply a safety factor to your CT. If you're getting a result of 104, basically double that. Assume that you need 208 just to play it safe. We don't have a lot of information on that, but in one of the Ohio evaluations that we did a pretty extensive study. Tom Waters was involved in that as well, showing that a safety factor 2 probably is pretty close to maybe what needs to be applied. And again, it just accounts for some variability that can happen. I'm not going to say a whole lot about this, but the new version 3 came out with another model that we're not going to be using today. It's a more advanced model, and this features, allowing modeling of intra and extracellular toxins through the water treatment plant. So think of your plant in terms of a profile as you add different oxidants or you have different treatment processes. It basically does a prediction on how well those toxins are being removed as you go through the plant. So it does require some inputs. Again, if you're interested in it, you can kind of look through it. It is pretty self-explanatory and the instructions are pretty good. So I think you can, most users can figure it out. And the important thing too is it's independent of the models that we're going to be using today. So it's really a separate feature of the spreadsheet. So summarizing, oxidation is definitely a key barrier for most water systems for cyanotoxin destruction. And in some cases, it may be the only barrier that the plant has. So I know Jamie, asked me about a situation about a small water treatment plant a few months ago at a camp. And really they didn't really have any physical removal. It was down to basically destruction of the toxin using chlorine. So it is a critical tool and an area to assess. Assessing the barrier requires an understanding of plant oxidation potential. So that CT concept, if you need to refresh your memory on that, there are slides that are in this presentation that you can review. Like many computer software programs and spreadsheets, Cyanotox is it's basically, it is intimidating to use at first, but with some practice, it can be a user-friendly tool for operators. And so we're going to really kind of start that process today, just to kind of get familiar with it, try a couple scenarios, and then encourage you to kind of use it on your own and apply it to your situation to get more experience. So we do have some small group workshops coming up next. And I'm going to stop sharing at this point. At least the presentation.
Hey, Jennifer, while Larry's doing that, are those of us, do we all keep our same number? So like I was number 4 for the last workshop. Is that throughout the entire rest of the day?
Yes.
Okay, thanks.
While Jennifer's kind of getting our rooms organized, I'm going to share just quickly a couple files with you. The workshop file is a Word document. Hopefully you've downloaded that. And it provides 2 case studies. There's a case study 1 and a case study 2. And it gives the background information on the type of cyanotoxin, the concentration in the intake or the source water, what the desired outlet concentrations are, and then other information that is needed to go into the spreadsheet. Each group is going to be focusing on just one of these case studies. The primary difference is case study 1, we have more of a conventional plant, has more treatment capability, including powder activated carbon feed. Case study 2 is a small package plant, shorter detention times, does not have the ability to feed packed. And they have a little bit different concentrations to work with as well, going through that assessing oxidation. So you will, from that information, input it into the spreadsheet and determine, what is the required CT for this particular plant. And then you're going to apply a safety factor to that. And then in the next part, based on that CT and knowing how much contact time we have, I'm going to have you calculate out what kind of residuals, what kind of chlorine residuals would be needed to meet that CT, and are they realistic? Can a plant do this? If you still have additional time beyond answering the questions, there are some questions about maybe how to squeeze out a little bit more CT from plants. The last part puts forth a scenario where both plants have the ability, do have the ability to feed permanganate at the front end. So if you did have that permanganate capability, how much reduction of that initial concentration could you get with feeding permanganate? So these are the 2 different scenarios of how you could use the spreadsheet. First one is going to determine your CT. The second one with permanganate is going to say, okay, knowing my CT, how far down can I drive my cyanotoxin levels with this application? And I apologize for that. I gave that whole discussion. I thought I was sharing my screen, but I was not. So I'm going to have to leave it up to the facilitators to cover my back there. All right.
How many minutes would you like?
I'm looking at our schedule here. So our next break is scheduled for about 2. So why don't we go with about 30 minutes?
Okay. We ready?
We're ready.